All right, so our primary topic today is the Bohr model of the atom. But before we get to the Bohr model of the atom, let's close the loop a little bit on what we ended Monday's lecture with, which was the photoelectric effect. And so remember, the last image that we had on Monday was the idea of the photoelectric effect in terms of I've got a piece of metal, I'm shooting light at it, and depending upon what kind of frequency of light, what kind of wavelength of light I get, some frequencies of light are able to take electrons and move them off of the piece of metal, others were not. And what that established was a threshold minimum. There was a minimum frequency that had to be met. Certain kinds of light, like red light, didn't meet that minimum frequency. The other kinds of light, as we saw in the video, the yellow, the green, the blue, all met the minimum threshold. But what we saw after that was, while yellow light was capable of ejecting electrons, the electrons that were ejected with blue light had much more energy than the ones that were ejected with yellow light. And so the overall effect that we saw was, okay, we've got this idea of threshold frequency. We've got this idea that light has energy. And we can associate those energies with those spectral lines that we saw, because we now know that light has energy, light has particle components to it. But that really doesn't explain everything about those spectral lines. Why are those lines in the locations that they are? And to understand that more fully, we start to investigate the hydrogen spectrum. And the reason we investigate the hydrogen spectrum is because, as you saw on Monday, the hydrogen spectrum is considerably simple. 4 spectral lines in the visible light region. Way easier to analyze than, say, neon, where you've got maybe 20 lines, or sodium, where you only have 2 lines in the visible spectrum, and they both happen to be yellow. So hydrogen is a good thing to focus on for those reasons. And there were ultimately 2 different series that were investigated. There was the Balmer series, and the Balmer series focused specifically on the visible light emissions. And the Rydberg, which focused primarily on the ultraviolet light emissions. Now, in both of these cases, we were able to generate a number, something called the wave number. And the wave number, which is the reciprocal of the wavelength, for a particular transition, could be predicted using this equation. And for general purposes, we call this the Rydberg equation. It goes like this. The wave number of light is equal to the Rydberg constant, 1.097 times 10 to the 7th reciprocal meters, multiplied by the difference in 1 over the energy level squared between the energy level that we start at and the energy level that we end at. So N1 here represents our starting energy level. N2 here represents our ending energy level. So if we look at those perspectives, what we can see is that when we go from one energy level to another inside of the hydrogen atom, we can predict how much, or we can predict the wave number of light, which is directly related to the wavelength, which we can then tie into frequency and energy. And the great thing about this particular equation was that it was very predictive. When it came to quantifying the hydrogen atom, the Rydberg equation did a really good job of doing so. And it not only worked for the Balmer series, it not only worked for the Rydberg series, but it would work for any energy transition that existed. But again, it had to be a hydrogen atom. So let's do a couple of practice problems here, just to familiarize ourselves with the Rydberg equation and how it is used. So just to reiterate, the Rydberg equation says 1 over the wavelength is equal to the Rydberg constant, RH, multiplied by 1 over N1 squared minus 1 over N2 squared. And recall that the Rydberg constant is 1.097 times 10 to the 7th reciprocal meters. So if I'm following an energy transition from the fourth to the second energy level, 1 over lambda is equal to 1.097 times 10 to the 7th reciprocal meters multiplied by 1 over 4 squared minus 1 over 2 squared. So pull out my calculator. Um, 1.097 times 10 to the 7th multiplied by the quantity of 1 over 16 minus 1 over 4 my wave number is negative 2.057 times 10 to the 6th wave numbers. I want to take the reciprocal of that. So reciprocal of that gives me negative 4.86 times 10 to the negative 7th meters. Now, the negative there is not terribly significant. All that means is that if I go from the fourth energy level down to the second energy level, the light is emitted. That's what the negative means. If the number was positive, that would mean that the energy had to come into the atom to make that transition happen. So if I'm going from a higher energy level to a lower energy level, I'm going to see energy given away by the atom as it does so. And that's going to come off in the form of light. The light that's going to come off is going to have 4.86 times 10 to the negative 7th as its wavelength, otherwise known as 486 nanometers, which would correspond to, I believe that's the teal line on that spectrum. From here, we could use our other equations to find frequency or energy just by taking that value and plugging it into an equation like this, for example. Now, if I was going to do that again, the negative here would only indicate that that energy is being emitted. All right, any questions about this example? All right, if you've been paying attention the past 3 weeks, you know what happens next. You're going to try it yourself. All right, what is the wavelength in nanometers for a transition between the first and fifth energy levels in a hydrogen atom? And then as a secondary question, how much energy would that atom need to absorb in order for this transition to occur? So take a few minutes, go ahead and try this out, and we'll come back and go over it in about 5 or 6 minutes. All right, so walking around, most of you are kind of on the right track, at least in terms of setting up the equation. Not all of you got all the way through the part of executing all of the calculations, but you should have at least got to that part there. Now, if you got to this point here where you had the wave numbers, and the wave numbers would have come as a result of doing this calculation, 1 over 1 squared, which is 1, minus 1 over 5 squared, which is 1/25th. You would have come up with 1.053 times 10 to the 7th wave numbers. Again, most of you got to this stage. Now, what you do after this stage, this is where a couple of you kind of ran into problems. How do I take the reciprocal of a number? And the answer is there's many ways to do it. One way is just to repeat the division. So you can look at this as I had 1 over wavelength is equal to 1.053 times 10 to the 7th over 1. If I'm going to flip the fraction to make it wavelength, I need to flip this fraction as well, which would mean 1 divided by 1.053 times 10 to the 7th. That's one way to do it. Most of you, however, are walking around with scientific or graphing calculators, and you should have a button that looks a lot like this. For some of you, it's in the direct functions, and some of you, it's in the secondary functions or the shift functions. That x to the -1, the -1 power in that mathematics is the reciprocal. So if I took 1.053 times 10 to the 7th and raised that whole thing to the -1 power, I would have got the correct answer there also. Correct answer is 9.497 times 10 to the -8 meters, which once we multiply that by 1 billion, because there are 1 billion nanometers in a meter, we get 94.97 nanometers. Now for the secondary problem here, how much energy would an atom need to absorb? This is where we go back to those equations that we saw on Monday. Energy is equal to hc over lambda, Planck's constant, 6.626 times 10 to the -34th, multiplied by the speed of light, 2.998 times 10 to the 8th meters per second, divided by the wavelength that we just calculated, the 9.947 times 10 to the negative 8th meters. If I do all of that, I get 2.092 times 10 to the negative 18th joules. And again, this would be an electron promotion, meaning that the atom absorbed energy, and in the process of absorbing that energy, it promotes an electron from the first energy level to the 5th energy level. And that's why our wavelength was positive. That's why our energy was positive here as well. If this was an electron demotion or a relaxing of an electron to a lower energy state, again, we would have seen negative numbers here. Again, all that the negative and positive mean is which direction is the electron going? Which direction is the energy going? Is the energy coming into the atom, or is the energy going out of the atom? Is the light coming in, or is the light going out? All right, any questions about this example before we move on? All right. So from the photoelectric effect and from these line spectra ideas, we can draw several conclusions. First of all, we understand now that electrons that are in the atom have specific energies. We call those energies quanta, and the whole process quantization. We know that when an electron moves from one energy level to another, it's got to either absorb a photon to get promoted to a higher energy level, or it's got to release a photon to go to a lower energy level, and the energy of that photon is equal to the amount of energy between the two energy levels. And thirdly, we now can see that the Rydberg equation will allow us to predict what the wavelength of light is for those transitions, with one important caveat. We have to be either looking at a hydrogen atom or a hydrogen-like atom, meaning having only one electron. So if I have helium and I take one of the electrons out of helium, and it goes from 2 electrons down to 1, then the Rydberg equation becomes viable. If I take lithium, which has 3 electrons usually, and I take 2 of them out, that one remaining electron in the lithium 2+ ion would behave according to the Rydberg equation. And so this stuff all kind of encompasses and couples into a model of the atom that was developed around that time called the Bohr model of the atom. Now, the Bohr model of the atom is a model of the atom that is still widely used and well known amongst even those of us who really don't consider ourselves scientists. When most people think of an atom, they think of something along these lines, where I've got a nucleus in the middle, I've got these electrons moving around that nucleus in kind of a series of concentric circle lines. Now, in the Bohr model of the atom, each one of those orbits represent an allowed energy level. So again, this is where we kind of integrate in that Rydberg equation, and we can use this to explain why the Balmer and the Rydberg series exist the way that they do. A couple of key terms surrounding the Bohr atom. First of all, a ground state. The ground state represents the lowest energy state of any particle. Now, for what that means for the most part, extending beyond just the hydrogen atom, it means that all the electrons in the atom are in their lowest possible energy levels. Doesn't mean that they all exist in the first energy level, because at some point the first energy level runs out of space. But all the electrons have the lowest energy possible. Now, if you're looking for these slides in the lecture notes, they're not there. They're in the post-lecture that's due tonight, or due Thursday night. So if you're looking for them, that's where they are. We should be able to pick up the lecture notes again in about 2 slides. The excited state would be one of those states where we've added energy to the atom, and an electron jumps up to a higher energy level as a result. This is an abnormal state for the atom. Atoms don't stay in their excited states for long. And usually what happens over time is that electron that is in that excited state will start to come back down to the ground state, because the ground state is where it wants to be. Now, to go from the ground state to an excited state, or the excited state to a ground state, electronic transitions have to occur. That's where the electron jumps from one energy level to another. And we see that coupled with some kind of change in energy. Either an emission of energy, if we're going from an excited state down, or an absorption of energy if we're going from a ground state up. Now, the Bohr model was constructed originally as a very limited model. It was meant to describe what was happening in the hydrogen atom and why those equations worked the way that they did. The Bohr model started to get extrapolated to other kinds of ideas because of its utility. And that's also where we kind of ran into some problems with it as well. So what are the fundamental assumptions? What did Niels Bohr assume when he made this model of the atom? First, he assumed that in a hydrogen atom, the electron moves around in a circular orbit. And so long as it stays in that circular orbit, its energy is at a constant level. Hence the concept of an energy level. All the electrons in that orbit hold the same energy. Now, inside of this model of the atom, there are multiple orbits, but only certain orbits are allowed, those that quantify to a specific amount of energy. And transitions can occur from one orbit to the next, provided that an equal amount of energy is either absorbed and the electron goes up, or released and the electron goes down. But those photon energies are always going to be equal to the difference in energy between the levels. So those are the fundamental assumptions of the model. And again, the model works pretty well, all things considered. But there are some issues with it. So first of all, let's talk about what's good about it. Using the Bohr model of the atom, we are able to accurately predict how much energy it takes to remove an electron from an atom. That's a process that we will refer to from here on as ionization. When an electron gets removed from an atom, we call that an ionization process. The Bohr model also allows us to expand our quantum mechanical understanding of the atom. And even though large parts of the Bohr model end up being kind of set aside because they're not useful to larger systems beyond hydrogen, a lot of the fundamentals of the model are intact and have been kept over time. And so that's one of the key strengths. We can start using the quantum theory to try to explain other ideas about atoms at the atomic level. Some limitations. First and foremost, it doesn't account for anything that has more than one electron. Now again, its original intent wasn't to do that anyway. But the limitation of the model itself is that we can't apply it directly to anything that has more than one electron. The second thing, that idea of those electrons moving around in those fixed orbits, that's not necessarily true either. It's a little bit, a heck of a lot more complex than that. One of the reasons for that complexity is because electrons don't actually behave in the sense that we think they should. Thus far, we've considered electrons as being particles. They're just really, really tiny, small particles that have a very small mass and happen to have a charge. Problem is, at that particular size, and given their motion, given their position, we actually see them exhibiting wave-like behaviors as opposed to particle behaviors. And so we started off this chapter with kind of a fundamental thought, light behaving as a wave. And then with the photoelectric effect, we smash that idea against the wall and we say, well, no, actually, light has this dualistic nature. It's wave-like in the sense that we can measure its frequency and its wavelength, but it's also particle-like in the sense that it has a set amount of energy and we can attribute that energy to a packet of light, the photon. We've also begun this chapter with the idea that electrons are particles. Small, negatively charged particles. But James Clerk Maxwell, Albert Einstein, a couple of other contemporaries of that time, Louis de Broglie, throw that kind of idea against the wall as well. Electrons actually exhibit wave-like behavior as well. And so this brings in another equation here. Now, don't worry about this particular equation in terms of, I'm not going to ask you to do any calculations with it. But what I want you to understand out of this equation is the following. Every single object that has a mass and is in motion has a resonant wavelength associated with it. That includes you and me. Now, for us, our mass is so massive, so large, that even if we're moving really, really, really fast, our wavelengths are close to nothing. 10 to the negative 40th. Kind of nothing. We consider that negligible. But if I have something that is small, like an electron, where it has a relatively low mass and travels at a relatively robust rate of speed, this wavelength suddenly isn't all that insignificant. In fact, this wavelength that is resonated by the electron as it moves has a wavelength that's relatively close to that of the size of the atom. And thus we have to account for it. And that's one of the things that made so many of the physicists of that time just stand there and scratch their heads about the whole concept. Because it's so odd. It's so out of whack compared to what they were expecting. And so I want to end with this concept. Now, We're going to watch another Professor Dave here. And what I want you to get after with regard to this is don't get hung up on the equations. Those equations are great if you have a big Calc 3 background and are taking physical chemistry at the college level. Don't get hung up on all that stuff. But follow the concept as best you can here. And then we'll kind of break it down and talk about it here as we close up the day.
Professor Dave again. Let's take a look at the Schrodinger equation.
He knows a lot about the science stuff. Professor Dave explains.
Through the work of Planck and Einstein, we were forced to accept that energy is quantized and that light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass. So objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of... Professor Dave again. Small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics. Except that rather than something like a plucked guitar string, an electron is a circular standing wave.
Okay, so just a brief timeout here. The waves that we were describing on Monday, light waves, those are linear standing waves. They have a resonant frequency, they have a resonant wavelength. We can measure each of those pretty precisely. What's different here, and he's going to get into the explanation of this, is that instead of a linear wave, we're going to think about electrons as a circular wave. So think about that idea of what the Bohr model ultimately stands on. Circular orbits. But instead of a circular orbit where it's going around in a linear kind of fashion, it's going around in a wave-like kind of fashion instead. So I'll let him finish up.
Surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron. Because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as we imagine a standing wave with one wavelength, and then two, and then three, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation.
Yeah, cut it there because he gets way off into concepts that you wouldn't be ready for another couple of years. But can we understand kind of the idea that's going on here? The Bohr model exists to show us this kind of idea. Now, again, this is where we had to kind of depart from the idea of Bohr itself. The fundamental assumption of that circular wave or that circular orbit wasn't correct because it wasn't accounting for the wave-like nature that had to be a part of that. And why we see differences in different atoms? Well, so for the first energy level, that first energy level has one wavelength within it. But that one wavelength might be of a different energy for an atom of lead versus an atom of beryllium. So they'll have different starting energies, they'll have different energies at each energy level, and that's why we're going to get different spectra from each one of them. Add in the extra interference from multiple electrons, each with their own standing waves, and that's why we're going to get multiple wavelengths. We're going to get those line spectra that have all of those different little emission lines, all of those different dark line matters. So the question I want to leave you with, I want you to think about between now and Friday, is given these descriptions, given the Bohr model, given what we just saw here with the idea of circular waves, how do we know where an electron is? How can we describe its motion precisely? Because that's ultimately what we're going to talk about on Friday. So think about that. Anyway, you're dismissed. Have a great afternoon.